Shalom, sir. Okay. Shalom, everybody. Thanks for the warm words. Thank you, everybody, for the moving experience and the fruitful experience to work with many of you during the last, I would say, 10 years since the conceiving of the Nano Center and the last 7 years when I served as the head of it. Well, actually, this is my first time to talk in the Nano Center conference, and it's about nanotechnology, of course, and nanotechnology have been praised for being very practical and technologically oriented, and it has been condemned for the same thing, for being too practical and too technological oriented, instead of doing real science. Let me reassure you, I'll talk to you about completely useless nanoparticles. And that will be the topic of my talk today. It will cover the last two works that I've been doing in nanotechnology, the completed works. And the common denominator is that there are taunting nanoparticles. Namely, some people have asked me, taunting is meta'atim, particles which do not behave as particles should be. One is a particle that doesn't really possess a stable and good properties, physical properties, as particle is supposed to be. And the other has to do about diffraction of nanoparticles, and you will see as we proceed. So here comes the first subject. It's about band gap fluctuation in bismuth nanoparticles. And this work has been done in cooperation with Yoram Zeltzer, our colleague at the School of Chemistry, with Yossi Larea, our TEM expert, and with a group of very good and dedicated students, Danny Grossman, Deborah Marshak, and Yuri Weinstein. Why bismuth? Because it has been promising to be a very good and practical candidate for enhancement the thermoelectric effect, namely getting use of thermal energy, either solar energy or other geothermic energy, and conversion to electricity. Bismuth by itself is a good material in this respect, and bismuth nanoparticles have been predicted to be extremely good in this respect, and this is something that Yoram Zeltzer and myself set as a target to really check whether this is a conceivable concept. Bismuth is a very interesting material in some respect. It's a semi-metal. For those of you who do not know the concept, it's a particle that in many directions doesn't show any properties of metal, but rather of semiconductors, while there are very specific directions where it can conduct electrons or electric current. It's highly isotropic, for instance, in terms of the effective mass of the electron. Namely, electron can be accelerated extremely fast in some direction and can be hardly accelerated in other direction. And according to theory, nanoparticles are semiconducting, highly anisotropic as well, and they are very good candidates to serve as a material with high thermoelectric Seebeck effect, namely high thermoelectric power. But then one starts to measure these particles, and even the most elementary measurements of all, just look of them with a TEM, with a transmission electron microscope, and one realizes very fast that at least at room temperature, they are extremely non-stable, and they show very erratic behavior by changing their shape, by appearing quasi-molten, by showing up. This is all subsequent picture of a single nanoparticle. Namely, they don't rest. There are typical rest periods and typical hectic transformation activity periods, and one cannot treat it as a very stable particle. some other TEM measurements show that even if the particles seem to be at rest, suddenly some atoms will appear, those red atoms hadn't been present here before, but just show up after a few pictures. In many ways, surface diffusion is extremely fast on top of those particles. So if this is the case, if they tend to change its shape, they must be unstable in other respects as well, and this is some projects that we have decided to develop in order to test the properties as a material. Let's take a nanoparticle, let's measure its properties. The technology which have made this possible is the scanning tunneling microscope. I guess that most of you know what it is. For the rest of the crowd, let me tell you that this is based actually on a transmission of electron in a tip through a very small vacuum barrier to a material, provided there's some energy levels that can accept those electrons, provided that the counter surface is not populated by electrons and electrons really can go through. This technology have honored Rohr and Binig here on the picture in Nobel Prize in 1986, if I remember well, by showing for the first time the theory concerning the rearrangement of silicon surface are indeed true, and that not only that one not can one doesn't need to depend on indirect evidences by scattering and things like that, but rather one can see almost with your bare eyes that indeed the surface have rearranged and has a very special structure. So this is, by the way, a very wonderful technology, because actually you can almost build it in your backyard, in your garage. It's quite simple. We have built, I'll talk to you later. Yes, it's almost like that. Really, it's almost like that. Anyway, what we will describe to you is what we have done with our home-built cryogenic STM to investigate those properties. Okay, so as you can see, we can see the topography of particles on top of a gold surface, and one can clearly define particles which are 8 or 7 nanometer large, and one can also distinguish very easily whether a particle is gold particles, sorry, here, a semiconductor particle, where one can see there's an energy gap. This is something which characterizes semiconductors, or rather whether this particle is a particle of gold, like what we see here, when the conductivity shows whether this graph, which describes the dependence of the current as a function of voltage on the tip of the STM, shows that this behaves like a resistor, namely that this behaves like a metallic particle. So what do you see when we put those particles on the test of fluctuation? What we have been doing is park our tip on top of one of those particles with larger stability than my hand, of course. I mean, just stick with 1 angstrom resolution on top of the particle and record this tunneling current as a function of time. And one could see is extremely large fluctuation in the current. So the first possibility, of course, is that we don't know to do the experiment right, but yes, we do. What you see here, the green curve, is what we see when we park the same tip and the same STM on top of the gold surface. And here the current can be stable for many, many minutes without doing anything. Namely, it's a good system and works well. But what we see here is very strong fluctuation. And then the question comes, is it really, what is the meaning of this fluctuation? We know that the particle have changed its property, but in what respect? So fluctuation of the current can result from two major things. One is that the distance between the particle and the tip changes, and it doesn't have to change dramatically. If you change this distance by 1 angstrom, the current can go up by 1 order of magnitude. And if the particle rearranges and really gets somewhat closer by atom diffusion or by rolling up to the tip, then the current can fluctuate up and down with such a range of current. And the other explanation, which is more appealing to us, that the particle as an entity changes its behavior and it has different physical properties. To check this possibility, what one has to do is to check what signifies and what characterizes those bismuth particles the most is to what extent they are semiconductors. And the property to measure the most typical property of a semiconductor is what is called in the physics and engineering jargon the band gap. Namely, what range of energy an electron which sits on some allowed level have to jump up in order to be there and to conduct electricity. The spacing between those two levels is called a band gap. There are no energy level where the electron can reside in between. So without going into technical details, with an STM, we can measure those properties. And what we could see is while measuring the current, and when the current jumps up, not only the current jumps up, but what we knew to do is also to measure the band gap, and the band gap indeed changes as the current fluctuates. So to make a long story short, and this graph summarizes a whole year of two very gifted graduate students in experimentation and measurements, what we can see that at 300 K, the particle fluctuates very much in its band gap. And not only in its band gap, but during a single measurement, it cannot be well defined. You see, we measure here something, and suddenly the measurement drops down and some new phenomena occurs. So at 300 K, yes, the band gap changes, but the particle is so erratic that our measurements is not very dependable. And then as the temperature goes slower and lower, still we can see that over a long period, there will be very stable properties, and the band gap will converge into somewhat single value. This is a histogram which describes the statistics of all our measurements at those various temperatures. And what we could see is that a single particle will stabilize on a single value or almost a single value, but even at 80 K, the lowest temperature of our STM, the particles are still liable. So in a way, this is a warning sign. It's a warning sign for other particles which are considered to be well behaved. And the reason that we see it so well with bismuth, because it's so operatic in its property, large scale, large changes in band gap. But it could be, and this is something that experimentalists as well as device engineers should take into account, that one can see fluctuation and one should be aware of fluctuation. Now, these fluctuations can be controlled. How much time do I have? 5? Okay. So just to give you the flavor, we can control this band gap and the stability by all kind of passivation layers. We stabilize the particle and will make it better behaves. I'll not go into details, just want to give you this flavor. Yes, particles are not small particles, have enough energy within them, especially at room temperature, to change, to fluctuate, to roll, even to change their phases. Now, one more point that I wish to make, and this is indeed in a single nanoparticle which was stable, and I won't tell you how I know that it was stable, but you can trust me or ask me later. We could see on the same nanoparticle at different places where we park the particle, we can see completely different band gaps. Namely, the same technology allows us really to see very large anisotropy in Bismuth nanoparticle, just for a comparison with some other nanoparticle, cadmium selenide core with an envelope of zinc sulfide. The nanoparticle is very stable in its band gap over many measurements. So these are the conclusions of the first half of my talk. Yes, nanoparticles can be very liable, can change their phases and forms. Be careful. It's especially noticeable with bismuth nanoparticle because both exhibit very profound band gap anisotropy, so it's easy to measure, and also because the energy landscape of the different phase is relatively shallow. So far the first part, and the second part has to do with particles which diffract. Quantum molecular interference, and the question, why do we really care for? The experiment is quite simple, but also the consequences are: take a molecule, large or small, take a grating, collimate your beam very well, and what do you see? You see diffraction. It's easy to say, it's very difficult to perform, but why should we care? We should care, first of all, I think, because, Ron, we know quantum mechanics, but we really don't believe it. We have to prove ourselves once and once again that it works, and put it in more and more extreme testing conditions. And then the second argument that people give, but it's somewhat superficial, because one can monitor van der Waals interaction with that. It's true, but this is not a good enough reason. You need to interpret the van der Waals forces to understand your experiment, but this is not a primary purpose. But the third, very important reason is that there are theories which tells you that other gravitational field, when the mass of a particle reach about 1 megadalton, then the wave character of a particle collapses. And actually, we are, I'll tell you in a moment who is we, in an attempt to get closer and closer to this challenge and really see diffraction of 1 megadalton particles. And the world expert in doing so is Markus Ernst from the University of Vienna, and he visited our lab 2 years ago, and he told us, look, we are stuck with our experiment because we do not know how to generate the really gentle gratings that we need. And MIT told us it's impossible to do, and I told him, yes, but we can do it. And I meant mainly Alex Zukernik, who was our expert in FIB, and he managed to produce those gratings with a periodicity of 100 nanometer and with the thickness of the film of 10 nanometer. And actually, he can do better than that, or he could do better than that, up to a periodicity of 40 nanometer, but this is not good for the experiment for the reasons that I will tell you. And what I'll tell you now about, in the next 5 minutes, I guess, is about an experiment that we have been doing in cooperation with Markus Ernst. As I told you, the Tel Aviv in Vienna, and the contribution of Tel Aviv was mainly the gratings that Alex Zukernik generated, and that Igal Lilach will produce even better gratings for the next generation of experiments. And my contribution also to putting a single molecule detection scheme, which has many benefits, into this experiment. So this is generally speaking, and I'll hurry up very much now. This is source of molecules. There's a tiny slit of 2 micron which collimates the beam, and there's a tiny grating with a periodicity of 100 nanometer, which makes the diffraction, and there's a surface on top of which the molecules land. And then if you apply the technology of a single molecule detection, you can detect the diffraction to within 20 nanometer in position. And we need those 20 nanometer really desperately, because the wavelength of the particle is several picometer, and the periodicity of the grating by physical constraints has to be about 100 nanometer. Namely that the diffraction angle, and Roy knows the problematics of that, is really, really tiny, so we need very good spatial resolution. So this is a little bit about history. The experiment began in 1961 in the diffraction of electrons, and now in 2011 we can make gratings with 100 nanometer and diffract molecules up to 1300 atomic mass units. I will skip details of the experiment. We don't have time. It's cooperation between Vienna, the experiment, and synthesis of fluorophores in the University of Basel and at Tel Aviv University, I've already told you. And first of all, can we really detect single molecules? Yes, we can. You see this is subsequent frames of 2 spots, and suddenly a spot disappears abruptly, and this is one of the characteristics of the fact that you really detect single molecules. We have other proofs that we do know to do that, and so once we do that, we can produce in 20 minutes and 3 months of preparation the following film. The music is from the Third Man, a movie that happens in Vienna immediately after the Second World War, if some of you remember it. So what you see is the appearance of the diffraction pattern, molecule by molecule, to form of a top of a fluorescent detection scheme and diffraction grating. Okay, I don't have time left, right? So I'll just tell you, yes, we can really differentiate very well the momentum of the particle. You can see this is of 500 atomic mass units, and this is of 15. We can speculate and analyze van der Waals forces between the grating and the molecules by analyzing the detailed profile of the diffraction pattern. We can reach, right now, that's a new experiment which is not displayed here yet, up to the 9th order of diffraction. What we see here is 0 order, 1, 2nd, 3rd, but we can go all the way to the 9th order. And the point is that this was a leapfrog jump of technology, which really enables us to propagate into the real challenge of detecting heavier particles up to 1 mega Dalton in mass, and really challenge some of the fundamental question of quantum mechanics. Thank you very much.
periphery
No, not really, because it's a projection, a two-dimensional projection of three-dimensional body. So in your analysis, you are much more sensitive to the periphery, right, than what happens in the bulk.
So let me ask that. One would see rearrangements of whether it's the band gap or fluctuations in terms of other fluctuations that are happening there. But does that mean that making the particles smaller and smaller give a better ratio of surface to volume that enhance these things? So this is why we can see them only in nanoparticles.
Yeah, I can tell you the other way, that when we enlarge the particle to about 50, 60 nanometer, they are much slower in showing these effects. To what? To do the which experiment? Dalton is atomic mass unit. Atomic 1,600 hydrogens in a box.
Hope we have time to talk some more. About the first experiment, so Bismuth, if you make a very big particle, meaning bulk, it has a negative band gap, I guess. Right? It's semi-metal.
So there are electron pockets and...
Right. So it's a negative band gap material. As you make the nanoparticles smaller than bulk, band gap principle should go from negative to positive.
That's right.
And, but where I was sitting, I didn't see any negative values on the plot. All of them are positive, correct?
Right, because the fingerprints of a change are more pronounced if you measure positive band gap. For negative band gap, all you see is changes in slopes of the conductivity.
Sure.
While in positive band gap, you can see quantified changes in the band gap that you can measure, and you could make histograms. And you can
but it would be interesting, nevertheless, to document negative band gap nanoparticles. I think it's an interesting thing in its own right.
In Bismuth, they will not fluctuate once they will reach this.
Yeah, even whether they fluctuate or not would be interesting to document negative gap nanoparticles and going transition from negative to positive. But I was wondering, really, my question is, could it be that the reason for the large fluctuation is not only because the initial band gap is very, very small, so fluctuations of a small number are more noticeable than fluctuation on a large number, but is it possible that actually some of the nanoparticles are charged and therefore the Fermi level is actually moving up significantly because one electron in a nanoparticle makes a very big difference if the initial gap is negative?
This is true, but then we will observe shift in the center of gravity of the ID curve. But this is not what we have observed. We have observed that the band gap
symmetric bonding
in most cases. When the measurements are at lower temperature, very dependable. The band gap just breathes.
Sure. Interesting. So you think all the particles are charged neutral?
It's probably not charging.
Thank you.
תודה רבה.